Imagine you are trying to unlock a treasure chest, but the key keeps changing shape every time you touch it. Frustrating, right? Now think of our DNA system, the blueprint of life. Scientists once believed it was always a simple double helix shape, like a straight key. But now we know that DNA can fold into special three-dimensional structures like G quadruplex DNA and triplex DNA. These act like hidden keys that can turn genes on or off, making them a powerful tool for gene therapy to treat diseases like cancer. But here's the challenge. These DNA structures are delicate and challenging to detail. The moment we try to study them, they can fall apart, like trying to hold a snowflake in your hand without melting it. So, how do we study something so fragile? I studied these fragile DNA structures using a powerful technique called native mass spectrometry, which allows us to study biomolecules while keeping them in their natural intact form, mimicking the pseudo physiological condition. But even mass spectrometry has a problem. It's like trying to catch a snowflake without melting it. That's why I use a new, highly sensitive and soft ionization method for native mass spectrometry called CVSSI. And this is a very gentle and controlled way to lift these DNA structures into the gas phase into the mass spectrometer. Almost like using a feather to move a butterfly without damaging its wings. Here, my method carefully transfers DNA into the mass spectrometer, preserving its shape and structure. This lets me accurately measure how stable these structures are in solution, how they fold, and how they might interact with drugs for gene therapy. So, why does this study really matter? If we can truly understand how these G quadruplex and triplex DNA work, how do they form and bind, we can design better treatment for cancer and genetic disorders. Imagine a future where we can turn faulty genes off like a switch or design drugs that precisely target harmful cells without any side effects. My research brings us one step closer to that future by solving a key problem: accurately capturing and studying these DNA species as they exist in the body. I'm not only just looking at the DNA, I'm unlocking its secrets to help shape the future of therapeutics for humankind.